is on Friday from 6 to 8 p.m. in the afternoon, evening. Homework party has been moved because the midterm would otherwise overlap with it, 2 to 5 on Wednesday. I think it's in the same room, but I'm not sure. Check the Piazza post. I'll be holding a review on Wednesday from 5 to 8 in 144. So if you don't know where 144 is, if you go to the lab and sort of keep going, go up some stairs and it's a little room, okay? We'll also be having additional instructor office hours both today and Thursday from 11 to 1 today. So half of that will be me, the other half will be Vasuki. The one on Thursday will only be 12 to 1 for now. And that will be both me and Vasuki. So please come to that, especially if you can't make it to the review. One other thing, buffer labs, if you've missed one of the touchscreen labs for whatever reason, you can make it up in a buffer lab. Check the Piazza post for that. Just out of curiosity, how many of you guys have done the last module of the touchscreen? A couple of you, okay. Well, thanks to Grace and Thomas for making fun songs with that. Just a review of last lecture, real quick. Let a recap. So what we did last time was sort of an overview of all the circuits that we've done so far, in addition to, so overview / review, as well as a little bit about circuit design. We did a few examples, including a difference. So we found what we called a differential amplifier, or a way that we could take a differential voltage measurement. And the other circuit that we did was a voltage-controlled current source. Okay? Does anyone have any questions from last lecture about the procedure or anything like that? No questions? Okay. Well, today we're going to do something a little bit different. We're going to design what's called a timer. So with a lot of these switch capacitor circuits we've talked about, like in the most generic example, we had some voltage source. I have to draw this bigger. Some voltage source. Some capacitor C1. And some capacitor C2. And we had these switches that switched in various phases in our circuit. We haven't really talked about those switches themselves and how we actually make them switch. Okay? So just for a minute, sort of extend our definition of a switch and call it what we call a voltage-controlled switch. So basically, we have this switch like this, and we define what's called a control voltage. Try something like this, V control, where if V control is above some threshold, call it VTH, the switch is a short circuit. Which basically means that the voltage across my switch, I'm going to call this V switch, is equal to 0. Okay? Now when the switch is open, or when the voltage is below this threshold, V control is less than some threshold VTH, the switch is open, and we say that the current through the switch I switch is equal to 0. Okay? Any questions on this so far? Does anyone know any examples of a voltage-controlled switch? A relay. Yeah, so a relay is an example of a voltage-controlled switch. In old power supplies, sometimes when you hit the current limit, you can actually hear the relays clicking inside. Also, if you use the turn signal in your car, I don't know if they're still relays, but you can hear it sort of clicking. That's where that sound comes from. It's a physical switch that's being opened and closed, and it's being controlled by a voltage. Any other examples? I'll give you a hint. You have billions of them in your pocket right now. Transistor, that's right. So transistors, relays, things like that, those are examples of voltage control switches. And in fact, in the lab, you are actually using a little integrated circuit that had a couple of transistors inside of it. And that's what you're using to switch your circuit in your capacitive touchscreen lab. Okay? But now the question is, how exactly do we want to make this circuit work so that certain switches are on in phase 1 and certain switches are on in phase 2, given the fact that we say, okay, they're voltage-controlled switches? So again, we have our circuit. The source. Capacitors C1 and C2, and here we want these two voltage control signals, VC1 and VC2. Okay, we want some voltages as functions of time. A lot of times we've talked about voltage sources just being a static voltage, but there's no reason why they couldn't vary with time as well. And in fact, you may have seen this in one of the labs messing around with the function generator. You could see on the oscilloscope that you had a voltage that was actually changing with time. Okay, so as a function of time, what do I want VC1 of t to look like? Yeah.
So the VC1 must stay constant?
Do I want it to stay constant? The control voltage here. Yeah? Do I want it to look like a pulse? So that's another suggestion. So let's say we have, as a function of time, we have a very short pulse. And we do it over and over again. Okay, we want to switch between the two phases repeatedly. Okay, and then what would we want the control voltage VC2 of t to look like? What should that look like? Do we want the same voltage as VC1? What would happen if these two switches are switching at the same time? It wouldn't work, right? We want only switch 1 to be on in phase 1, and we want switch 2 to be off. In phase 2, we want switch 2 to be off, and we want only switch 1 to be on. Okay? Now I'm just going to tell you this is a little bit beyond the scope of the class, but it's actually very difficult to make pulses like this, especially very narrow ones. Okay? So it's a good suggestion, and in principle it would work, but it is challenging. So instead, what I'm going to suggest is we have a square wave. Okay? So we have some switching waveform that looks like this. Here's my voltage as a function of time, where this voltage that it gets to, the max, just has to be somewhere above the switching threshold of my device, whatever it happens to be. So for a transistor, that could be anywhere from 300 millivolts to 1 volt, or for a relay, it could be considerably higher depending on what exactly is built into that relay. But that's something that I want, right? Now, if I'm given this as my first switching waveform, what do I need VC2 to look like? Yeah. The opposite square wave, right? I want any time that switch 1 is on, I want switch 2 to be off. And any time that switch 1 is off, switch 2 to be on. There we go. Just like this. Okay? So it's just the opposite, right? Everybody clear on this? Now, how can I generate this waveform? How do I make an oscillation like this? Does anyone have any suggestions at all? Yeah. Wait, yeah, op amps are involved. It's a good suggestion. Yeah? Probably capacitors, right? So capacitors are the one circuit element that we know about that has some dependence with time. Any other ideas? So what happens if, let's say I give you the following circuit. I tell you, I take a current source and I attach it to a capacitor. My source, here's my capacitor C, and my voltage Vc of t, voltage on the capacitance as a function of time on the capacitor. We found out a couple of times now the voltage on this capacitor, assuming that we have 0 charge at time 0, it's just my initial condition, will increase. And the slope will be the current divided by the capacitance. Okay? Now, how could I turn this general idea into some oscillation, some periodic waveform? Yeah.
So the voltage would stop when it's equal to a certain point. So that means we can set the VTH for VC1 as that threshold.
So the suggestion is this will stop after a certain amount of time, but I never told you what's inside of this current source. As far as you know, this is perfect, and this will go on forever. Yeah.
If you reverse the current so that you get a downward slope?
Yeah, what happens if I reverse the current? So I do this for some amount of time. So this is what my circuit looks like in, let's call it phase 1. Then in phase 2, I take that current and I just flip it over. Here's my capacitor. Here's my Vc of t, my capacitance. Now, if I do that switch, if I call this part of the wave phase 1, and I call this afterwards phase 2, what's going to happen is this voltage, instead of going up forever, I switch and I go the other way. Now the slope will be the same, just negative. Negative Is over C, assuming that the current value is the same. And it'll go down. I'm going to call that phase 2. Okay? Now I can repeat this over and over again forever. Right? If I keep doing this, if I keep switching between phase 1 and phase 2, and both phase 1 and phase 2 are a fixed amount of time and an equal amount of time, I'll end up with a wave that kind of looks like a triangle. Okay, that's going to keep going. That's a good suggestion. But we're kind of stuck again, because if we want to switch between phase 1 and phase 2, we need that voltage-controlled switch again. It's kind of like a little bit of a chicken and egg problem, right? So let's draw out the whole waveform and the switching circuit that we would need to get this to work. So we have two current sources, one that charges our capacitor and one that discharges our capacitor. Okay, here's Is, pointing the other direction. We have our capacitor C, voltage on the capacitor Vc, and we have some switches This one's on in phase 1. This one is on in phase 2. And that'll give us this triangular waveform, this repetitive, periodic, triangular waveform. Now, what do I mean by periodic? Does anyone know what that means? Nobody knows what periodic means. Yeah?
Fixed length of time, like between periods?
Yeah, so it means it repeats after a fixed length of time. Meaning, if I plot this waveform, again, assuming that phase 1 lasts the exact same amount as phase 2, and these two currents are the same, function of time, my capacitor voltage, assuming we start at 0, will look something like this. Okay? And to call it periodic means that this same thing repeats after a fixed period of time, and we call that period usually t. Okay? And again, these slopes are IS over C and negative IS over C. Okay? Now the first question is, how can we take this result and turn it into the square wave that we had earlier? You have a suggestion? We could use a comparator, yeah. So let's do that. Take our same capacitor charging and discharging circuit. Oops, wrong way. Phase 1, phase 2. I take this and I connect it to a comparator. V, let's call this V sub S. That seems fine. So here's our capacitor, right? Now where do I want to place this voltage? What voltage do I want to choose to make this triangular waveform turn into a square waveform? 0. Okay, so that's one suggestion. What's going to happen if this voltage is 0? So we have, as a function of time, we have the capacitor voltage, and that looks something like this. Again, this depends on the initial condition. Now, if we pet the threshold of the comparator at 0, what would happen here? So that's right here. What would happen in that case? Yeah?
You always get the positive V rail.
We would always get positive V rail, right? Or in this case, actually, because this is minus and plus, we'd actually always get the negative V rail. So here we have plus V rail minus V rail. Suppose that they're equal. So we'll just always be at the negative rail. So that's not a switching waveform, not quite. Where else could we put it? Yeah? We want it to be about halfway, right? Or in this case, exactly halfway. So if it's exactly halfway, right down the middle, the output of this, I'll draw it over here as well. If it's below the threshold, if my capacitor voltage is below the threshold, this source voltage here, excuse me, not the threshold, then the output will be the positive rail, okay? So if we do this, will be positive V rail, and then in the other phase, we'll be at negative V rail, and back up to positive, back down to negative, V rail, minus V rail, okay, as a function of time. Now, what do you notice about this waveform? It aligns pretty nicely with my triangular waveform, right? Let's just shift it a little bit. How then could I apply this to my switching circuit, which is also right here? Yeah, you have a suggestion?
I was going to say we probably need to add another voltage source to get it from negative V rail to 0.
You could do that, yeah. You could add a voltage source to get it from negative V rail to 0. Alternatively, what you could do is set up a different initial condition on your capacitor and basically shift your triangular waveform down. Okay, those are equivalent. Is that clear to everybody what that means? So basically, we want this switching waveform, rather than to be centered about some, what's called a bias point, DC bias, we want this to be centered around 0. So our goal here should be to make it so that this, I'll try it a little bit fainter. We would like it to be like this. And why do we want that to happen? Why is that desirable? Yeah?
Because then your VS can just be 0 and then you save power.
So first of all, our VS can be 0. We don't actually save any power because it doesn't have any current through it. That VS is just static. But what it does is it makes it so that our switching waveform is exactly aligned with the output of the comparator. Okay? Does that make sense? So what we want to happen is, we want some voltage that controls this switch, we want some voltage that controls this switch, and we want this oscillation to come from the circuit itself. We want a self-sustaining oscillation. Okay? Yeah?
Feed V out into the back, basically a giant feedback loop.
That's right. We want to feed V out, which is over here. So this is V out as a function of time. We want to somehow feed V out to these switches. Okay? That's our goal. In fact, we actually have to end up feeding them to these switches as well as to change this voltage down here. That way, we can make these switches exactly align with the square wave that we want to come out. Okay? So that's all nice, but it kind of defeats the purpose, right? How are we even going to get these switching waveforms to start? How can we make this happen? In other words, what's another way that we can generate this triangular waveform? And it's a circuit that we talked about yesterday, towards the end. Do you guys remember it? Not the difference, the other circuit. We had the following circuit, right? We had some voltage, Vs, some resistor R, and we put, here's V out, we put some load in feedback across this amplifier. And what we found was, aside from some pretty extreme conditions, this current through the load was equal to V source divided by R, no matter what that load was. This was our voltage-controlled current source, right? Okay? You guys remember this? Do I have to analyze it again? Nope. Okay, so how can we use this to generate our triangular wave? Yeah.
Well, now we can have two voltage sources that have opposite signs and just switch, not really switch, now it's just turning them on and off.
Yes.
To get the current to reverse.
So now what we can do is we can take a voltage source that switches between plus some voltage and minus some voltage, and we can plug that into our circuit, have a capacitor here, and that will give us that triangular wave. So we'll switch between a positive current and a negative current. We don't need those two current sources anymore. All we need is this one voltage source, okay? So let's say I make that voltage source and I'm going to draw it as a square wave inside of the little circle. We have some resistor. and I put my capacitor here. Okay, so the current, here's my Vs as a function of time. This current is going to switch between a positive current and a negative current. So we have Vs of t divided by R, and we know that that's the current because this, by the golden rules, is 0. Okay, so what's that waveform going to look like? We operate under the assumption that we can somehow get this switching waveform. So here's Vs of t and t. So this we get magically for now, and we'll see how we actually can figure out how to get that from the circuit itself. Here's the current through the capacitor, the current through the load as a function of time. And it's going to look like this, right? You're going to go up until you reach this point, and you're going to go down, then up again, and then down. Yeah, this aligns. Perfect. You see how that works out? Now, what is the output voltage as a function of time? I'm sorry, this is not the current. This is the voltage on the capacitor. The current and the voltage in the capacitor are the same, right? Just scaled by a resistance. This is the voltage in across the capacitor. Now, what does that mean that the voltage at the output is? Yeah. 0 minus the voltage on the capacitor. Why is that? We look at our circuit, and the way that we've defined the current by passive sign convention across the capacitor is like this, right? So the output voltage by KVL is 0. We know that this is 0 because of golden rules of op amps. 0 minus the capacitor voltage as a function of time is equal to V out. So basically, V out is just going to be minus VC. Just going to look something like this. Okay? Is this clear to everybody? V out is a function of time. Now again, how can I take this and turn it into that square wave that I wanted? Well, let's do the same suggestion. What we did before was we had our circuit. Here's my source voltage as a function of time. Here's my resistor, my capacitor. Let's attach this to a comparator with some plus V rail and minus V rail. Let's call this V output C, the voltage output of the comparator. Now, what is that going to look like if I superimpose it onto here? How's that going to look? Well, if the voltage VC is positive, if it's greater than 0, then it's going to be minus 1, right? If it's less than 0, it's going to be plus the rail, okay? So here we have, when it's below 0, we have a waveform that looks like this. Then it's going to switch down and go up again. Right? So how does that compare to our switching waveform here? It's not quite there, right? Something's missing. We're going to have to figure out a way to make this comparator align with our switching waveform. How can we do that? give you a hint. Let's try analyzing just by itself the following circuit. Take our comparator, has V-rail and minus V-rail. I'll try a little bit closer in here. We have our input voltage. And instead of tying this to some reference, let's take it and connect it to the output of the comparator. Now, what kind of feedback is this? This is positive feedback, right? Now, let's suppose that this V-in is switching somehow between plus and minus V-rail. What's going to happen when this voltage is high, when it's positive V-rail? What's the output going to do? It's going to go to minus V-rail, right? This voltage is less than this voltage, so this is going to go to minus V-rail. And it's going to stay there, right? We have the condition that the output voltage is some large gain A times the difference in these two potentials, which means that if this one is negative, or is a positive voltage, the output will be negative, and it will stay there. Okay, now what happens if we go from V-rail to minus V-rail? As we transition between positive and negative, the output is going to do the opposite, right? It's going to go from minus V-rail to V-rail. Okay? Now, if it's minus V-rail at this node and plus V-rail at this node, again, we're stuck in this position, right? No golden rules. We're not in negative feedback. These two potentials do not need to be the same necessarily. So we're stuck, okay? And that's how this positive feedback process works. So let's now attach this circuit to what we had from our timer from before. We've got our source voltage, Vs, and that's switching. We have our constant current source, voltage-controlled current source. And here we have now our positive feedback comparator. Okay? Now this is we'll call this minus Vc, because this voltage again is Vc of t. And this we'll call V out. Now let's plot all the waveforms that we have in our circuit. Now it turns out that it's actually a requirement if you want a stable oscillation to have positive feedback of some kind in your circuit. In other words, you have to have zero phase margin is what it's called. So we have our switching waveform as a function of time. It looks like this. Our capacitor voltage, again, is it's going up, then down, then up, then down. Okay, not drawn exactly aligned here. There we go. Now so this is Vs of t, Vc of t. What is the voltage at the output of my comparator going to look like? Again, so basically what we have is VRail minus VRail. And here we have a triangle wave centered about 0. Okay? Now let's say that this triangle wave that I've drawn never actually gets to VRail. So let's say VRail is up here, and minus VRail is below here. What'll happen at the output? What's that? Will it reduce itself to become the amplitude? No, so the gain is very high of this comparator, so it's going to get stuck in one position or the other. Now, which position is it going to get stuck in? So let's say we start out with this voltage being high, let's say. If this is a large voltage, then this is going to go to the negative rail, right? By default. Now, if you never get back above the positive rail, this voltage, V plus minus V minus, will never be less than 0, and the output will be stuck at the negative rail. Okay? Never be greater than 0, so you'll be stuck at the negative rail. Okay, is that clear? On the other hand, if instead, so let's say VRail is somewhere in the middle, and minus VRail, somewhere in the middle of my capacitor waveform, capacitor voltage, what is this output going to look like? So we have our capacitor waveform that looks something like this. So let's suppose down here, this is below VRail, minus VRail, excuse me. This is below the negative rail of the comparator. What is the output going to be? So this is less than minus VRail. What's the output of the comparator going to be in that situation? What is V plus minus V minus? What is the lowest that V out could possibly be? Negative VRail, right? So what's greater? Negative VRail or something that's less than VRail? Negative VRail is greater. So this is going to go to the positive rail, right? So we'll be stuck up here until what happens? At what point will this switch? When will VRail at the output reverse from what we had previously? When V negative, the voltage at the negative terminal, becomes greater than the voltage at the positive terminal. That is when we will switch, okay? And that's exactly when we get here, right? So we switch, we go down, and then we keep going until the opposite happens, right? We get here, we go up, and we continue that forever, okay? Now, if we happen to make it so that VRail happens exactly at this point here, it turns out that our waveform will look exactly like VS. Okay? Is that clear? Let me draw it out again. Here we have our positive feedback amplifier, and I'm going to call this voltage V in as a function of time. This voltage V out, here's positive V rail, here's negative V rail. As a function of time, I have V in of t, and I know that that looks like a triangle wave, right? And what I said was, I get exactly to the voltage V rail when I go to the top, and I get exactly to the voltage minus V rail when I get to the bottom. Okay? If this is equal to V rail, we already know that the output is going to go to negative V rail, right? Was that going to work? Yeah. Which means that if we're up here, we know that the output voltage, and I'll draw that down here, is going to be negative V rail. Okay? At what point will that switch? What happens when this is, instead of being V rail, this is negative V rail? What will happen to the output? So technically, the two voltages will be the same, but let's say we just go a tiny bit lower. Okay, just a tiny bit lower. Then the output will switch to positive V rail. So as soon as we get here, we switch to the positive rail. And in fact, that'll happen going in the opposite direction as well. So here we have V rail, minus V rail, plus V rail. This aligns exactly with our capacitor waveform, right? So that's how we can end up using the output of this positive feedback comparator to switch our capacitor. Okay, switch the current in the capacitor. What's the catch, though? What is this V in? It's V out, which is equal to what in terms of the capacitor voltage? It's negative VC. So V in here is equal to negative VC of t. Okay? So what can we do to remedy that? We can use an inverting amplifier, right? So let's try that. So we have our switching voltage here, our constant current through our capacitor, and here we have Vc of t. Here we have minus Vc of t. And then we're going to put this through an inverting amplifier. Which means that the output of this inverting amplifier is just going to be equal to Vc of t. Now what we can do is plug this into our positive feedback circuit. Plus V rail minus V rail. And now what can we do with that? Now we know, if we plot our waveforms again, I'm going to have to fit 3 of them on top of each other. So this could be we want our Vc of t to look something like this. right? We also want minus Vc of t to look like this. Right? What is the output of my comparator going to be, that positive feedback comparator? It's going to look something like, okay, when the output is high, or excuse me, when Vc itself is high, the output will be low, okay? So we'll start out, in this case, high, and then as soon as we get to this point, we switch low. We go all the way until we reach negative V rail, we switch high, then to here until we go low again. Okay, so this is my V out as a function of time. How can I now use V out, which is aligned exactly with my capacitor switching waveform, in my circuit to create a self-sustaining oscillation? Remember what we started with, right? Our very first suggestion was we take this voltage, you have it, yeah.
You would plug it in back to VS.
I plug it back into the very input of my circuit. So in total, my circuit will look something like this. We have this resistor and capacitor. We have the inverting amplifier. Here we have our positive feedback comparator, V rail and minus V rail. We take this and we make it our source voltage, Vs. Okay? So let's go through this circuit really quick and see whether or not this actually works, right? Let's say Vs is high. That means Vc of t, so this, let's say it starts out high. Vc of t will be increasing as defined in this way, okay, with a slope of Vs divided by R divided by C. Okay, so the current divided by the capacitance. That's the slope of that line. So the output voltage here, which is minus Vc, is going to be dropping. Okay, we put that result through the inverting amplifier, and this output right here will be increasing. Now, at what point will this switch? When this voltage here, which is equal to Vc, here's Vc of t, same voltage. When that hits the rail, Vs of t switches low. So high, low. Yeah?
I think you mentioned this earlier, but isn't it technically like when the voltage gets like very, very slightly above the rail?
Yep, so that's a good point. That's what I was about to get back to. It only happens if I get slightly above the rail. If they're exactly equal, the output isn't really defined, especially for a comparator. Okay, for an op-amp, technically it's 0 because there's some gain times V plus minus V minus. If this were a proper comparator, it goes crazy when the voltages are very similar to each other. Just as a side note, a comparator and an op-amp are actually very different circuits. We use an op-amp as a comparator, but generally that's not the case. Okay, it's just a side note though. So you're right though. We have to get very close to V-rail and then go a little bit above it for this switch to actually happen. So how could we remedy that? How could we make it so that we don't necessarily need that? Does anyone have any suggestions? What would happen if we made it so that these two comparators had the same rail, V rail here and minus V rail here? Excuse me, these op-amps, not comparators, they're in feedback. Here we have V rail and minus V rail. And here, instead of using that same voltage supply, I have some V rail minus some small voltage, V small. And here I have minus V rail plus some small voltage V small. That then guarantees that I can get above this voltage, meaning now I don't have to make it all the way to V rail. All I have to do is make it to V rail minus V small, or in the other case, minus V rail plus V small. And so that guarantees that this switching actually happens. Okay? So that's one suggestion. What's another one? What is the reason that I have to get all the way up to V rail? It's because this voltage down here at the positive terminal, if this voltage is low, the output will be at V rail. The output then has to make it all the way up to V rail. What happens if I make this voltage less? Then I don't have to go as far, right? How can I make that voltage lower without changing the rails of the amplifier? A voltage divider. That's a very good suggestion. So let's do that. So same circuit that I had before. Here I have my inverting amplifier. And here I have my positive feedback amplifier, or comparator, and I add to it some voltage division. So if we have still the same rail on every amplifier, and also over here, V rail and minus V rail, you take this resistor all the way over here. Now what sets the condition for when my voltage switches? So here we've got R and R, let's say. What sets that condition? R2 over R1 plus R2. So suppose that we start with, this is a low voltage. The negative terminal of this comparator is a low voltage. And it's going up. Okay, it's increasing. So this voltage VC of t is some negative value and it goes up. At what point will this comparator switch? When VC of t reaches V rail times R2 over R1 plus R2. It's just a voltage divider, right? So if this is low, this voltage will be V rail times R2 over R1 plus R2. Okay? The moment that the negative terminal reaches that point, I switch. Okay, and I go to the negative rail. So once I reach this V rail times R2 over R1 plus R2, which I've written very small, but you can see it down here, you switch. Okay, so the output voltage, which was previously low, suddenly goes high. Okay, and we didn't have to get all the way to the rail. So that was a good suggestion. That works out pretty well. So now we have it done, right? We've made a circuit that self-sustains an oscillation. Now the question is, what is the frequency of this oscillation? Does anyone know how to compute that? Yeah. It depends on how fast my capacitor is charging or discharging. That's right. So looking again only at our positive feedback circuit, We know that VC of t is just a line, right? VC of t looks something like this. It's a line that increases up until I get to some voltage. At that point, the output here, which is being fed back, I've only cut this part of the circuit out. The output here, V out, the moment that that switches, the slope of my line switches. Okay, so I go from this and I go down up until I reach the negative point here, and then I switch back. Okay? Is everybody clear on this? So here's the slope. This slope is set by whatever V out is divided by R times C, where again, R is just the resistor that I have that's setting the current in the capacitor. And C is the capacitance, right? So the current is Vs over R, the capacitance is C, the slope of this line is V out over RC. Okay? At what voltage will this switch happen? How high of a voltage do I need to get to before my output goes from being a positive voltage to a negative voltage? So at what point, let's call this voltage Vx. If this voltage is low, meaning Vc of t is low, so this part of the switching waveform, Vc of t. If it's low, what will Vx be equal to? Vx will be equal to the positive rail, right? Sorry, it'll be Vx will equal the positive rail times some voltage division, R2 over R1 plus R2. Okay? What happens as Vc of t increases? As I go up, 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 what voltage do I need to get to before that output voltage switches the other way? Fundamentally, Vc of t needs to get higher than Vx. Okay? So if Vc of t is low, Vx is V rail times R2 over R1 plus R2, and V out is V rail. Now once I reach the opposite condition, once I say, okay, now I get to Vc of t is equal to a little bit more, so V rail times R2 over R1 plus R2, plus some V small. It just gets above it. What's going to happen to my output voltage? V out is going to go to minus V rail. Right? It's going to switch to the opposite rail of the comparator. And Vx is then going to become minus V rail times R2 over R1 plus R2. And that's going to repeat forever. So I'm going to keep going up and down with my capacitor voltage. My output voltage is going to be fixed high, low, high, low. Okay, and it's going to keep going. Okay, so that's the voltage I need to get to. This is V rail times R2 over R1 plus R2. That's this voltage. What does that tell me about the frequency or the period of my switching waveform? So the period, the way that we defined it, was how long it takes for my wave to repeat. My voltage is a function of time. How long does it take for me to repeat? So that's the period, t. It's some amount of time that it takes for me to get from this point down here to the same point in my wave. So one triangle. The next triangle is the next period. the frequency is equal to 1 divided by period. Okay? So what's the period of my switching waveform? Knowing that I need to get all the way from down here, so this is minus Vrail times R2 over R1 plus R2. How long does it take my capacitor voltage to get to Vrail times R2 over R1 plus R2? And again, this is just equal to, let's call this Vx. The difference of the voltage divided by the slope, right? It's just a line. We're going from one point to the next. Okay? Just to draw it out one more time. I have to get from here, this voltage is negative Vrail times R2 over R1 plus R2. I have some slope that I know. The slope of this is Vrail divided by RC, and the voltage that I get to up here is positive Vrail times R2 over R1 plus R2. And so by your suggestion, the time that it takes, this time, t, let's call it tau, just not get confused, here's t. That time is equal to the difference in the voltages. Well, it's a function of the distance of the difference between these two voltages, so that's 2 times Vrail times R2 over R1 plus R2. And how do I use the slope? If I do it, I'll mess it up, I promise you. So someone is going to have to tell me. This time tau is a function of the difference in these two voltages. If I have a higher slope, will tau be larger or smaller? Smaller, right? So we divide by the slope of this line, which is Vrail divided by RC. Okay? Now what do you guys, just a real quick note here. What do you guys notice about the units of this expression? Let me cancel out Vrail, so we end up with 2 times RC times R2 over R1 plus R2. What are the units of this expression? So the resistance cancels out in R2 over R1 plus R2. And what am I left with? R and C, right? It turns out that resistance times capacitance actually has units of time. It's kind of a, so ohms, farads, and this turns into time, seconds. And the units actually, it turns out that they work out. Okay? That's why maybe you've heard of RC time constants before. R times C has units of time. And that actually happened before when we talked about settling in a capacitor. We had that exponential e to the minus t over RC. So the units of that actually work out as well. It's e to a unitless quantity. Okay, cool. So we found tau, but that doesn't really answer our question. What is the period now as a function of what we just calculated, tau? The period t is just equal to 2 times tau, right? It takes us 1 tau to get from the negative voltage all the way up to the positive voltage. And it takes another tau to get back down. And so our total period, t, is equal to 2 tau, which means our frequency, f, is 1 over 2 tau, which is equal to 1 over 4 RC times R2 over R1 plus R2. And that tells us how quickly our waveform is switching between positive and negative, okay? Any questions on this? Are any of you guys musicians by any chance? Do you have any idea of like common frequencies? Like what's middle C in frequency?
I know that 400 hertz is about an A.
Yep, so 440 hertz, I believe, is an A or a C or something.
And then twice that is another A.
Twice that is another A, right? So it's logarithmic. As I double the frequency.
So divide that into eighths to get that kind of normalized Bach scale.
Right, yeah, so that gives you the scale. I'm just trying to get ideas for frequency, okay?
Right.
So 440 hertz is a sound, okay? And it turns out that a human's hearing range is about 20 hertz to 20 kilohertz, 20,000 hertz. Human hearing. Okay? So what we could actually do is make these timers. If we take this output voltage and attach a speaker to it, we can actually make sound. Now it's a square wave, so it wouldn't sound very good, but this timer circuit is the basic principle behind like electronic synthesizers. And way back, like in the 50s, there was a guy named Moog who made synthesizers and keyboards that you have probably heard of if you listen to any classic rock from the 70s. But one other circuit that I want to talk about is another way to create a timer. I was kind of hoping that someone would suggest this when I asked how to make a timer. And it's based on the following principle. You guys might remember when we talked about op amps, we had this sort of classical feedback model. We had this summing node, which was the difference between the positive and negative terminals of my comparator. I had some gain, and I took this and I fed it back like this. So here I had my input voltage, V in. Here I had some difference between the input voltage and my fedback voltage. And here I had my output. Now in negative feedback, is there any way that we could have an oscillation? Is it possible? Unless we have some external switching going on, meaning we don't have a self-sustaining oscillation, it's actually not possible. You cannot have an oscillation from negative feedback unless your op amp is unstable. So it is theoretically possible, but it's a little bit much for this class. So what we can do, and what we actually did in this other circuit, was instead of feeding back some voltage that's of opposite sign of our input voltage, what if we add something that's the same sign? Okay? So we've turned it into positive feedback. And let's for now assume, just take an example. We have some gain of 1, and I'm going to feed this back. So here I have some voltage input, V in. Let's say the output voltage starts at 0, just for the sake of argument. We'll have, I have plus plus here. The input voltage will show up here, right? The output then will be V in, again, because I'm just multiplying it by 1. I feed that back, and now here I have V in plus V in. So this becomes 2V in. Okay? 2V in times 1 is equal to 2V in. Feed that back, now I have 3V in. And this is going to continue on forever until my output voltage goes to infinity, or in a real world, it will go to the rail of the amplifier, okay? So at some point, I cannot go any further. So is this an oscillation? No, not really, right? It's not exactly doing what I want it to do. What about instead, if I take this and I flip the sign of this 1? So instead what I want to do, I want something that toggles between two different voltages. So here again I have my summing node, and instead of a +1, I have a -1, in the hopes that I can have something switch between two voltages at the output. Here's my V in, here's my V out, and here's my feedback. So here I have V in the first stage, let's say V out is 0, so this will be V in again, and the output is negative V in. I go back to my node, V in minus V in, darn it, didn't work, right? This becomes 0, and then we're stuck there. Or are we? What's going to happen if this is 0? So this, in the second stage of my circuit, is equal to 0. 0 times -1 is 0. If I come back now, I've got V in plus 0, which is equal to V in again. My output is minus V in. So I'm oscillating between these two values. Now just one quick test of maybe your Module 1 understanding. What can you tell me about the eigenvalues of this system? One of them is 0, okay, so we get something that cancels out, so that's possible, but that's not really the answer that I was looking for. -1, right? Each time I apply my pump matrix, which is represented by this system, I flip the sign of my output. So an eigenvalue is -1. In the previous one, where I had that exponential explosion, where my output voltage just kept going up and up and up, and I couldn't stop it. What do I know about the eigenvalue of that system? One of them. It's greater than 1, or less than -1. Actually, I know that it's greater than 1 in that case. You're right. Okay, cool. So circuits, again, comes back to this concept of linear algebra once we get into control circuits and feedback. Okay, it's all linked together. Okay, so now how can I actually make this circuit? So first of all, what will be the frequency of this oscillation if I just leave it like this? Really fast, right? Is there any delay built into this -1? No. So this oscillation will be extremely fast between minus V in and 0. Okay, so what I can do here is add delay. Okay, that's one way I can deal with this problem. Now, what circuit do we know that adds delay? A capacitor. And what else? What else do we need to create a delay? A switch, okay. We need one other thing.
Like inverting op-amps.
We don't need an inverting op-amp, it's simpler than that. It's a circuit that I covered a little while ago, yeah. A resistor. If I take this circuit, resistor, capacitor, if I have a switch at my input, if I have a change in voltage at my input, the output here, so here's V in, the output voltage will start low. Let's say we were in steady state before, and instead of immediately jumping up, we get this exponential increase, which means that we have some delay built into our circuit, okay? And it turns out that this expression is, if this goes from 0 to some value, let's say Vs, it turns out that this is equal to V out is equal to Vs 1 minus e to the minus t over Rc. So we have some delay. And if we make it so that we have some comparator voltage in the middle here, sometime after this has occurred, we'll get a switch that looks like this. So the actual wave that came in, this switch, Vs, switched at some time t equals 0. Over here, here's t equals 0. And this, if I put my comparator, V comparator, there, will switch a little bit after. There's some time delay. Okay? Yeah? Would it be true if I didn't have a resistor? If this resistor were 0, and I just had a short circuit, would there be any delay in my circuit? So let's draw that faintly, really quick. Let's say this resistance is 0. What is the output voltage? It'll be exactly the same as my input voltage. There's no delay here, because it's just a short circuit. So let's put that back. So now we want this comparator value to give us something that switches between this and this, okay? And we need positive feedback as well. So we've got the negative terminal, and we're somehow going to feed back, or no, the positive terminal. We're somehow going to feed back to that positive terminal. So if we build this circuit, we have some delay, R and C. We'll plug that into, I want this on the negative side, excuse me. Negative and positive. If I have some switch that happens at time t equals 0, this voltage will look like this. Here's time t equals 0. And it'll happen at some point after the actual switch here happens. If I then feed back an inverted version of that, what'll happen is, depending on whatever that delay is, I'll have a sign flip in my voltage. Okay? So I want to take this output somehow and feed it back to my input. Okay? I actually got it wrong. It's like with a USB stick, you always get it wrong twice. Plus minus. This is positive feedback back here. And this is some threshold voltage, some V comp. Okay? So what's going to happen here is, at time t equals 0, we get, let's say we start at some high voltage. At time t equals 0, the voltage here, V plus at the positive terminal of my comparator, is going to increase slowly, right? At some point, I'm going to reach the comparator voltage. Let's say we get there right there. Once I get there, did I get it wrong another time? Yeah, I did. I want to switch, right? I want to switch to the other side. So this output voltage then, as soon as I get to this comparator value, will go down. Okay? The minute that that happens, that voltage drops. This one is going to go the other way to compensate. So it's going to keep going down until it reaches 0. And the output voltage will just stay at 0. Bummer. Okay, so we were close, right? We saw it at the beginning, but it didn't quite work out because we fell below this comparator voltage. And the way that we can actually remedy that is using what's called a ring oscillator, which is taking that same circuit in principle, but now, instead of using a single comparator and a single RC circuit, what we can do is chain 3 of them together. If we do this, we get a stable oscillation. Okay, it turns out that you need an odd number of comparators in this case to get a stable oscillation. Okay? Any questions at all? That is the end of the circuits module. You're all done with circuits until your midterm, I guess, and the final. So study. That's it for me, though. Next lecture is Vasuki.